So, hello everyone. Welcome to today's SFI seminar. And today it's my great pleasure to introduce our speaker today, Weishi Chen. And Weishi Chen is a PhD at Penn in the electrical and system engineering, advised by Professor Chen. And he received his bachelor's degree and master's degree in mechanical engineering from National Taiwan University in 2011 and 2013, respectively. And his current research interests include embodied intelligence and bio-inspired robotics behavior and integration of systems. So, and now just a few instructions for this talk. So for the audience on Zoom, you can just unmute yourself or just type of questions in the chat. And for the audience in the room, so there's a speaker at the front of the room. So make sure like everyone on Zoom can also hear the questions. And last but not least, so we have food and we have snack bars and also drink at the end of the meeting. So feel free to grab them, but we do ask you to eat outside because technically eating is not allowed in this room because of the school policy. Okay, so now without further ado, take it away.
Thank you, Sam. Hi, I'm Weishi Chen, and today I'm going to take you on a tour on origamis and robotics. So, okay, can you see this? Yeah, awesome. All right, so today the title of my talk is going to be building dynamical robots with origami fabrications. So I believe everybody have folded a crane when you're little, or at least see someone folding a crane before, a paper crane. And people has been fascinated by origami for a very, very long time. And for mathematicians and for engineers, what's particularly interesting is to understand how one piece of paper can fold into such like diverse shapes. And so one thing we're very interested in seeing is this thing we call the crease pattern. So a crease pattern is something on a piece of paper that assigns folds onto the sheet of paper, telling you which edges can be folded in a mountain or like 180 degrees and valley like in negative 180 degrees. So with this kind of crease pattern, we kind of understand how things fold from that flat shape into like a 3D structure. And so there becomes a question about how can we design a sheet material such that it can fold into different kinds of objects with different properties. And by properties here, I'm talking about maybe different shapes, 3D shapes, or if you prefer like a 2D shapes, or different kind of mechanical properties, which includes like different stiffnesses or different rigidities. And so the first part of this problem, different shapes, has been studied throughout the ages, and Robert Lang came up with this tree maker that says that if you have like a topological tree, you can map it onto a crease pattern and fold into this kind of shape, and then you can remodel it into some like crazy figures. And then Eric Demain and Tachi, they made this thing called the Origamizer, which says that any kind of topological surface or manifold, we can fold it with one piece of paper. The catch is there's going to be a hole somewhere in the 3D structure. But these two things show us that there's a tons of programmability with the shapes of the object and how to fold one piece of paper into it. Now, Cynthia Song, Dr. Song, she made this kind of new pattern called the REBO pattern. And originally, it's going to try to mimic the surface of a pattern. And then we attach some sort of tendon in these REBO structure, the REBO bellows, and realize that it really behaves like a spring. And the way you line the tendons will affect how this thing goes. And so this comes up to the second part of the origami design problem. Can we design also different kind of mechanical properties? So we want to, a lot of people have been studying this question. Can we fold a sheet material into any object? In this talk, I would like to talk about, can we fold a sheet material into a dynamic robot? And so what does a dynamic robot do? By dynamic robot, I'm going to focus on robot that has this kind of at least two different phases with hybrid dynamics that will allow it to manipulate energy in a way that converts kinetic and potential energy. And so this is going to be the content of my talk. I'm going to first talk about the REBO structure and then talk about two applications we made with these REBO structures. And then I'm going to talk a little bit more on more origami modules and then how to make them all into one single robot with one piece of paper. So first, we're going to talk about the REBO module. Like I said, REBO module was developed in Dr. Song's lab, and originally this was made to mimic a given surface, a rotational surface to be precise. And we realized that once we change the parameters here, the alpha angle, it will affect the cone angle, that's the beta here, and will result in different kind of slopes. So the steeper this slope is going to be, it turns out that it's stiffer. And so we took these this design and applied different cone angles, and we try to perform some sort of mechanical test on it. The first thing we realize is that although these are paper coated in plastic, they're really resilient, and we try to compress it and uncompress it for 2,000 times, and there's no brokenness in the structure, and it still works the same. And you can see that the force and displacement graph will sort of converge into some region after the first few cycle, which is very common in like origamis, because the first few cycle is basically the plastic deformations. And so then we test out these different kind of modules. Yes.
So what are the different colors in the left plot mean?
Yeah, thank you. So the red color means it's the first cycle, and then as time goes, it converges to the blue cycle. Thank you. So then we try to test the different force and displacement graph of the of these different cone angle, and we realized that the 2/3 of the whole travel, it really is a linear relation. So it's kind of like a Hookean spring. And so we fit it out, and it turns out that it follows the cone angle really well. And we have selectability on how much, how stiff we want the whole structure to be. On top of that, we also put two modules in like concentric matter. So on the right top side, that's a module with two layers. On the outside, it's a transparent layer. And by putting two modules together, we actually increase the stiffness by adding the stiffness together. So we have this beautiful origami springs. What can we do with them? The first thing we did is we made a juggler out of it. And this is how the juggler looks. We have three springs in parallel, and there's a force sensor on top, and it's driven by tendon pulling by the a brushless motor. And first we try to find the kinematics to it. It's a one-to-one relation, and we try several different workspace. It turns out that the more you want to compress, the more error it will be, but it still has a pretty nice trajectory tracking ability. And the next thing we want to do is, can we actually make it to do dynamical task? And so here we want it to juggle a ball. Here the ball you see is actually a shot put that is 1 kilogram. And by the way, the three REBO spring add up to about 100 grams. And so I thought, sorry, 30 grams. And so this has the ability to really push way heavier stuff than itself. And so this is our state machine. Whenever it detects it touching the force pad, it just releases what it compresses. And so can we actually control it? That's the question here. And so first of all, we try to put the ball, drop the ball from different initial condition. And it turns out that it did converge into a pretty steady apex height for the balls. So that's a pretty good controllability. Then we also try to juggle different kind of balls. So we juggle balls that are 1 kilogram, 1.4 kilograms. We also juggle medicine balls, which are balls that has sands in it, and it takes away tons of energy. Normally, if you drop the ball, it would not bounce back. But this graph shows that the medicine ball also juggles to a certain height, indicating that we put enough energy into the whole system. So here's a video.
So you're folding all these by hand?
Yes.
It's amazing.
Yes. This structure takes about 10 minutes to fold. And although it took a little bit practice, but my undergrad picks it up really fast.
So why are you like wrapping it in this plastic?
There's two reasons. The first one is to increase the stiffnesses. The second is to prevent it from buckling, because the outer shell sort of prevents it to going into the bistable position. Yeah, so we have this REBO juggler, and then the next question is, can we turn it upside down? If we turn it upside down, it will be available to push itself up. And as we demonstrated before, it has the ability to manipulate different kind of environment. like shot put, which is really stiff, or medicine ball, which is really soft. And so we try to make a hopper. This time we decreased the poly size. We realized that last time we had it too big, and the workspace wasn't enough because the spring just is too stiff. And so we use this almost the same state machine and build a hopper and made it bounce on this vertical rail. The first thing we want to show is that we're trying to read the force, the force sensor from the toe. And once it detects its contact, then we release the tendons that was pulled by the motor. And this release will release potential energy into kinetic energy. So again, we try different kind of compressions. We try compressing the spring for 14 millimeters up to 28 millimeters and try to see the relation between the jump height and the compression. And it turns out that it is kind of linear and we can control it. And also there's an error bar there, but you can't see it because the error is just too small. And so we also try different initial conditions, dropping it from different height, and it still goes into a certain apex height. This is why the error bar is so small. But hopping is not just like vertical. Can we do fore-aft hopping like the video that I showed you to begin with? Where like a giant thumper, like thumping around? The answer is yes. Since we have 3 degrees of freedom in our hopper, we can use 1 degree of freedom to sort of swing their legs forward and then push it backward when you want to jump forward. So here we implement a REBO style controller and try to see if different touchdown angles by adjusting the origami limb will give a different velocity. And the answer is yes, we can do that. And so we implement it with a very easy step control to try to make it hop faster and then stop, and then and then flip the velocity and then stop. And okay, so I will show you the video, but this is the snapshot of the forward hopping, fore-aft hopping. Up to here, we're using the force sensor in the toe to try to act as a trigger for the whole system. But we are also kind of, this is a side project. We want to see if we can actually take off the force sensor and still perform a pretty good controlled hopping. And so we took the concept of the proprioception, which we use the information provided by the actuator itself. It can be encoders, it can be some potentiometer that is embedded in the system. And it turns out that if we compare the sense that it thinks it touches something because of the error tracking of the encoder, with the original ground truth, which is the force sensor, there could be some error. So that error is something that we need to think about. But think about this: we have a tendon-driven machine, and whenever this thing hits the ground, the tendon just lose tension. So how can you track an error with no like tension at all? And so here, what we did is we're using the fact that P control loop, the P control that we implement on the motor has some sort of error, some sort of offset. And whenever it touches down, this offset just goes directly back to the nominal position. And so we measure that exact moment that it goes to. So it acts like a as a trigger. And it turns out that it still performs pretty well. There's some, I'm sorry, this is the drop delay. It performs pretty well, although there's some kind of delay in the system. It's like a 5 millisecond delay, I believe. It's still enough for the system to behave like what we originally had. We only implement this proprioception in the 1 degree of freedom just to show that you can hop without any sensors. So here's another video that we did with this hopper. All right. And so we built a robot limb basically out of origami. Can we build a whole robot of a piece of sheet papers? And then you would ask, why would we do that? Why would you build like a robot with one piece of sheet? Here's some reason why. The first is that if we have a sheet structure or a shell structure, if you make a scaling argument on that, if you scaled it up, the mass that's increased will be less than the mass that's increased in like a solid or a traditional robot scaling. So the affordance for the actuator is actually going to be less. And this is actually like an ongoing study that I'm also doing on like different size, different scale, and different structure. And this is the first reason I think if we want a family of different size robot, this will be a really good way to show that we can build a large family of robot with probably the same actuator without needing to size everything. And so the second one is that the sheet material actually has this ability to change stiffness. So we can make this like triangle prism structure, which we know it's very strong, and we can build like paper bridge out of it. And we also know that if we don't do anything with a sheet of material, it's very flimsy and very soft. So if we have the ability to tune the stiffness in the whole structure with one sheet, sheet material will be a very good choice to do that. The third reason is that topologically, this crease pattern is a flat surface. And so we can sort of print like our circuit on it and then fold it. And theoretically, it's easier to manage than doing tons of wires. So these are some of the reasons why I think building a robot with origamis are nice. Here I would like to propose a problem statement. Can we build a robot out of a piece of paper? Might be too hard, might be a too large problem. So let's start with a serial robot or a kinematic chain. So here I propose if the DH representation of a serial robot is given, can we make a piece of crease pattern that can fold into a kinematically equivalent robot to this one? And as you may or may not know, the DH parameter is a way to describe where the joint is. But unfortunately, it's not unique going the back way. So if someone give you a DH parameter, you probably will design a very different robot than what the other people will do. And this is what we kind of had in mind. Can we make some structure that the green part is kind of like a joint and the white part is the linkage? Can we design like a kinematic chain with just one piece of paper? And so the first thing we need to do is introduce more origami modules. So we have the REBO structure, but now I'm going to introduce you more. And this time I'm going to tie it with the spatial transformation. Here, this is what I call a Prism Tube. This tube is basically just sorry? All right, thank you. So this tube is, you can see there's like a two hexagon on the edge of this tube. Here, from here on, I'm going to describe this tube as like a rigid transformation, where you take the bottom polygon, where we call the proximal polygon, and transform it into the upper one, which we call the distal polygon. And so now the origami problem kind of transform into like a trajectory planning problem. But let's not get ahead of ourselves. We assign some sort of frame onto each polygons, so that later on these frame will be useful for us to do the connection of different modules. And the second one is the twist. So we have like a translational transformation. Now, can we have a twist one? So we can. This is just twisting the polygon along its forward direction for some angle. And this angle, because a polygon is actually a symmetrical object, so we can rotate it however we want. We just need to make sure that the actual degree matches the shape of the polygons. And the third one is a rotation along like a axis that's perpendicular to your forward direction. And this is what we call the elbow fitting, which again, we can treat it as kind of moving forward, turning, and then forward a little bit. Or if you look at the beginning and the end position of the polygon, you realize that this is actually just steering with a constant radius that can be shown in the transformation matrix on top of it. And so these are the structure that cannot move. Now let's talk about the structure that actually will provide some sort of motion. This is what I call the prismatic joint, where the blue part is actually the REBO structure. So the REBO structure here is surrounded by a wall. That's the lower part there. So this wall will constrain the REBO structure to only move in one direction, because the REBO structure that we describe is actually a very high degree of freedom structure. And so again, we can write out the rigid transformations. And then we have the Revolute joint, which allows rotation along an axis that's perpendicular to my forward directions. which in here, you probably notice, oh, this actually look like a milk carton. And it is inspired by a milk carton, but this is actually a generalized so that it can apply to any polygon shape. So up to here, we can apply all the structure in any polygon shape structure. But the Revolute can only be applied into like even side polygon. And what about the stiffness? Can we change the stiffness of the structure? The previous one is a REBO structure. So yes, we can change that by changing a parameter on the cone angle. But what about the Revolute joint? Can we actually change the stiffness too? So I want to focus on this red square here. There's rectangle here. By changing this by changing the pattern in this red rectangle, replacing it with a recursive set of pattern, we're actually increasing the thickness that's in that system. And as you can see in the middle figure, that's an example of a layer 4 recursive sync gadget that kind of look like the milk curtain, but it's going back and forth. And because of that, we actually increase the stiffness. And so on the right-hand side, we can see that the stiffness of the whole structure being bent down is linear. And we can sort of predict how much stiffness we need for the structure. Theoretically, we can go on to infinity, but it will be very hard to fold. So now we're going to talk about how to put all of this together. We talked about viewing this origami structure as some sort of rigid transformation or a path planning problem. So here is 2 polygons that I want to connect in a 3D space, 3-dimensional space. It has its own position, it has its own orientation. How do we connect this 2 stuff? It turns out that this is kind of a well-known problem. It's a Dubin's path problem. So we implement the Dubin's path, and we can find a path in 3D space that is consists of a circular rotation with constant radius, and then going forward for some sort of distance, and then do another rotation. To construct this path, the two polygon needs to be at least 4 R's apart. R is mentioned here. And so we can write out the transformation matrix here. This is the transformation of this Dubin's path. And it turns out that if you take a look at these matrix transformation, you realize that they are the transformation matrix that I proposed with the previous structures. So we can just replace the transformation matrix with the origami modules that we have. So first of all, we have this elbow that is in red. And then we have a green one, that's the translational, that's the tube. And then we have another blue one, that's another elbow. However, because there is some offset in the twist, so we need to add back the twist. This is not captured in the Dubin's path because it does not care about the twist. And so we add a yellow twist module there to twist the frame back. And so this is the way we are going to connect different modules. And now the problem is how do we synthesize this whole serial robot? Let's say we are given this cylinder joint, a cylinder manipulator that's consists of a prismatic joint that's drawn in a rectangular shape, and a cylinder shape represent the Revolute joint. We for each of the origami joints, we can assign frames up to it. So these frames can be placed on the structure in a way that as long as there is C-axis, and the ABC is the joint frame, as long as the C-axis align with the Z-axis of the joint frame, that's for the Revolute, and as long as the prismatic's Z-axis goes along with A-axis, then as long as they are on that line, we can achieve the same kinematic motion. So this is why we talked about how this is not a unique solution. And the way we think about this problem now can be think as first of all, it can be a packing problem where there's tons of different, we call it a joint spare in space. And how do we assign these joint space so that they are all some sort of distance apart, because we need this distance for the Dubin's path to work. And we also don't want this space to go crazy large, so it's a packing problem. It's also like a Dubin's, it's a travel salesman's problem. So how do we go from one point to another point? And so here we first place one joint, and then we want the second joint to be d distance apart. And in order to place the next one, we group this into a sphere, a new sphere. And we have the new joint to be some distance apart again. So this will allow every joint to be at least d difference apart. And then we can add another joint, but this time, in addition to that, it needs to be d distance apart from the joint, the sphere that encloses all the other joints. We also need to make sure that the edge that it creates with the previous one has a distance apart from the entire sphere. So this is to make sure that it will not self-intersect. So with all these things together, we propose this Kinegami program. And so this Kinegami, it's on my GitHub, so you can play with it, download with it. Once you have this specification in a DH parameter form, it automatically selects the right module and put it into the joint assignment and the link generation. And the output is a very long crease pattern that you can fold into a robot that is kinematically equivalent. So here's some result. This is a cylinder joint or a cylinder manipulator. It consists of a Revolute joint with a prismatic joint where the joint axes are called linear. And so you put in the DH parameter, you get this long stripe of crease pattern. You fold it and you glue the two parts together, the edges together. And here, this is the result. You can see that the lower part is a Revolute joint that can revolute along Z1, and Z2 is actually a squishy prismatic joint. And here's a planar manipulator where all the three Revolute joints are where all the axes are in parallels. And this is a little bit more complicated. This is the spherical wrist. In order for them to not collide with each other, you can see that this crease pattern is quite long and it looks a little bit weird shaped. But this algorithm guarantees that at least one robot exists, and you can build it with the same kinematically equivalent motion. And but the thing is, it guarantees one robot. It's not guarantee like a good or like a small robot or a compact robot. So if you have like some sort of knowledge to what you think each joint should be, you can also use them as your input. So this is a 6 degree of freedom Kuma arm. And the left-hand side is the robot that's generated by the algorithm. And the right-hand side is something that I just input myself. That's the frame of each joint and their orientation. You can just enter them. And it turns out that the paper needed to make the right-hand side is 2 meters long. And the one on the right-hand side is 1.3 meters long. And so it's significantly shorter, but it does require some sort of knowledge to how you think each joint could be connected to each other. And there's no guarantee that it will work because of the Dubin's path generation. So here is the robot that we want to test out. This is the robot with the actuation. We started with just one joint and one actuator. And this whole robot took us about like 5 to 10 minutes to design, and it took about 2 hours in total to finish. And this is a catapult. In addition to the joint and the fingertip, we can also assign different points in the 3D space that we want the structure to pass through without leaving any joint. That's the B1, B2, B3, and B4. So you assign those points, we get a crease pattern that will fold into this shape. And we use Arduino and a linear a servo motor for our actuation. And what we're trying to show is that the servo motor is slow, but because the fact that we use the compliance in the paper, so we can actually store energy into the joint and still perform some sort of dynamical motions. And so here's a video of it's releasing a ping pong ball. Okay, so that's what we did for now. Just to talk about the conclusion, we made a REBO spring. We sort of made a lot of mechanical testing on it. We achieved repeatable dynamical task with juggling and hopping. And we have this proprioception detection for tendon-driven robot in general. And we have this new set of parameterized catalog of origami module, and we can use them to form a robot that can give us a one-piece origami mechanism that is kinematically equivalent to your input. So our future work is, can we actually tune the stiffness on air? So in real time, if we can tune the stiffness, we can do a lot of new crazy stuff. And the next part is, can we add some different actuation into the folded structure, for example, some sort of active materials, so that we can do a sheet fabrication without implementing a servo motor. And this will greatly increase the power density of the whole robot. And perhaps it can do some crazy stuff like bouncing between like branches. And so here, this is an origami quadruped that we think we can build, and it's made of one piece of paper. There's like a REBO joint in each of the legs. This is the robot lying on its back, and hopefully it will work. We don't know yet. And yeah, thank you very much. And this is the team that helped make this happen. There's the collaborators are on the talk, and a lot of people provide their precious insight to the whole project. Thank you very much.
Okay, so I'm going to start with the first question. Yeah, so I guess I'll start with the first question. So back to the comparison of the crease pattern generated by your algorithm and the crease pattern that you generated yourself. So so the crease pattern generated by the algorithm is a lot longer. Is that because that algorithm is imposing those constraints?
Yes. Yes. So in order for a Dubin's path to be generated in our constraint, it needs to be at least 4R long. And as the structure goes longer, we actually made it more conservative. So it's getting longer and longer when you increase each additional joints. But if you know that you can design a robot that is, it will be some sort of distance apart, you can actually just input the position of the joints. And that will be a lot shorter.
So question, Chen. So do you expect the rotational joint to have the same fatigue life or repeatability as the REBO joint?
I do. I do think it's going to be long as well, but honestly, I don't really like the idea of using the thickness as the increasement of the stiffness. The way we introduce different stiffness in the REBO structure is by tuning the angle, and because this angle is actually affecting the bucklings of the surface, so the energy is actually stored in the surface of the in the facet, the planes, where the energy is really stored just in the fold for the Revolute joint. So I have come up with some new kind of Revolute joint, but I haven't put it on here yet.
Another question here.
Yes.
So I know, I think, so first of all, this is an awesome talk, really.
Thank you.
There are some ideas, I guess, in Origami about having kind of a modular approach. So maybe I have multiple pieces of paper, I can fit them together somehow, and I can build something. Is that something that could come into play here?
Yes, exactly. Yes. So here we sort of have a very strict rule about using just one piece of paper. But in reality, you don't really care if it's like one piece of paper or many sheets of paper. And in reality, you don't have this kind of long paper. Mm-hmm. And the way we fabricate it is we use several different paper and we glued it too. But you can think of it as it's still easy to have these different paper, send it to you, maybe you order online and it send it to you, you fold it, and then you just match them together. So yes, I do think like modularity kind of folding will be helpful with that. And that's probably a better way to go for a quadruped than just like a one piece of paper folding into a quadruped, because it's actually really annoying to fold.
Out of those structures that you design, so if it's like X and Y and the axis, so I think so you have a mechanism for, is that Revolute mechanism to rotate by X and Y axis? So do you have a mechanism that could rotate by the axis?
Oh, that's the twist.
That's a twist?
Yes.
Oh, okay.
Yes. And also the X and Y, you kind of need some space because it's steering with turning. So you can't turn in space, in the spot, because then it will intersect with itself.
But with the Z, but with the twist, when it's actually rotating, is it like
okay. So you're talking about the joints thing, the thing where it can move, right? The thing where it's freely rotate in 1 degree of freedom.
Yeah.
Yeah. So the way is you take that thing and you flip it, so that the axis matches the Z axis, and since you have this polygon that you want to connect, you can just connect it that way. So it doesn't really matter where the rotation is. As long as it's 1 degree of freedom rotation, you can connect them. Yes, for example, here, the cylinder, oops. Okay, I'm just going to show this. The cylinder manipulator, the joint down there is Z axis. So you kind of need some additional space for it to go past it and then go upward. Okay. Yes.
So I'm curious about the spherical joint manipulator that you showed. If you were to switch the order of some of the joints, do you think you get like a more compact robot, or is it kind of like you were saying about X first instead of about Z first? Do you think you get more?
Maybe we did not take a closer look, but I actually did try to play with universal joints. That's 1 less degree, and we try to use the algorithm to solve this, and we did it ourselves. I still feel like doing it by yourself will have a better compactness. Yeah.
Yeah,
So,
although if you do it by yourself, you have to know how to do it
you have to
make
know.
it compact, which I don't know that I would, having not worked on these. So I'm curious, I guess with that, my follow-up question would be like, what are there principles that you know from doing it yourself that you can apply to like refine the algorithm afterwards or something?
No, I have not done that yet, but that's a great improvement. So a way to go is to add some sort of optimization wrapper around the whole system to manipulate the joints so that they can be a lot more closer to each other without violating the constraints. So yes, that's something we thought about that, but we haven't done it yet.
Yeah, all right, very impressive.
Thank you.
I think I'll have the last question. So it's like back to that REBO structure that you discussed. So it seems like that REBO structure always need like a supporting structure, whether to keep it in place, whether it's like a kind of bar or like a base. So is it possible to take that structure out, or like is it possible to make it like auto balance itself?
I don't think so yet. I think that's a thing that I will dream of doing, but I'm not there yet. But I think a better way to go first is to make a quadruped. So there is like 4 sets of legs, so I don't need to think about the balancing issue. And I think that will be a better way to go because monopad jumping is very hard in the 3D space. Not to talk about compliance mechanism jumping in 3D space.
Cool. So I think we are at the end of our talk, and yeah. So thanks everyone for attending, and thanks Wei-Shi for giving the talk, and it's really impressive work. So yeah, let's give another round of applause.